Now we study this question. We have the following theorem. Chain rule. So let G be differentiable at A, and F is a map from U. U is an open subset of Rm open. Now let F be a map from U to Rl, the third Euclidean space. So if the image of G contained in the domain of definition of F, that is U, and F is differentiable at the point B. B is the image of A. The result is that then the composition is differentiable at A, and the derivative of the composition is the multiplication of F prime B and G prime A. Okay, so the differentiability of the composition is natural. This conclusion is natural, but we need to give a proof. And I want to say something about the final equality. What's this equality? So F composition G is a map from RL, right? Because G maps into RL. So the composition is a map from the ball BRA to RL. Okay? So the derivative, therefore, because the ball is n-dimensional, therefore the derivative on the left hand side of this equality is L by a matrix. How about the right hand side? So we should know that this is an equality of matrices. So the left hand side we have already know that it is an L by a matrix. So how about the right hand side? The right hand side, the first term F prime B. F prime B because F is a map from n-dimensional open set U to RL, to L dimension. So the first term is L by M matrix because F is m-dimensional to L-dimensional. Therefore, the derivative is L by N. Similarly, our G is n-dimensional to m-dimensional. So the G prime A is M by N matrix. So the two matrices in the right hand side are L by M and M by N. Their multiplication is also L by N. It is reasonable to say whether it equals to the left hand side because they are the same type of matrix L by N. The result is that they are equal. So this is the equality in this theorem. Okay. Now we also want to have another investigation to the equality. So if we use X to denote the independent variable, X runs in the BRA, and we use U to denote the intermediate variable, that is a point in U, in Rm, and we use Y to denote the dependent variable, that is our map G map X to U, and F maps U to Y. Of course, the composition maps X to U and then to Y, finally to Y. Okay, so the three matrices in the equality of this theorem is the Jacobian matrix. The first is the Jacobian matrix of Y with respect to X. The first term you can consider as the Jacobian matrix of Y with respect to X. And the second term, the first term and the two matrices on the right hand side, because f prime b, f is map U to Y, so f prime b is the Jacobian matrix of Y with respect to U. And similarly, G prime A is the Jacobian matrix of U with respect to X. So roughly speaking, our equality can be written in this way. Okay, but what's the dy dx is? What's this? We only know that if x and y are real valued. So we know this, the partial derivative of y with respect to x. Now we use this notation to denote the Jacobian matrix. This red box equality dy dx equal dy du dx is another form of the result in the theorem. More precisely, it should be written in this way. More precisely, this means dy dx is dy1 dx1 dy1 dxn dyl. Y has L components, dx1 dyl dxn. Okay, this is dy dx. This is for dy du, that is dy1 du1 dy1 dum. U has m components, so dyl du1 dyl dum, and du dx du1 dx1 du1 dxn dum dx1 dum dxn. Okay, so this is a more precise form in component wise for the equality in the theorem, in the conclusion of the theorem. So we have three forms of the conclusion. Apart from the differentiability of the composition, as to the equality, we have these three forms. The first form is what's stated in the theorem. The second form is the red box formula dy dx here, and the final form is more explicit in component wise. Okay. So now we consider a special element of the matrix. For example, we consider this element here. An element here is the case row. The row number is k, and the column number is I. Maybe I use another color for column. Is I. So how to determine the k row I column element of the metric dy dx? By the multiplication law of metric multiplication, we see that this element is the multiplication of the case row of the first matrix on the right hand side, that is this row, multiply with the corresponding i's column of the second matrix. Here is also k, here is also I. Okay, so this element is determined by the kth row of the first matrix of the right hand side and the i's column. So in formula, I write this page. In formula, this means sigma. No, sorry, not sigma. dyk dxi equals sigma j from 1 to m dyk duj dxi. Okay, of course, all these partial derivatives should be taken value in the correct point. Here, the matrix on the left hand side should take value at the point A, and the matrix at the first matrix on the right hand side will take value in B, and also the second matrix will take value in A. So in our this equality, we also has B and A, B, A. Okay, so this is the component-wise result for the chain rule. From this chain rule, but we also usually we omit the point ABC, AAB. We omit this point. We simply denote the result in this way. You will judge whether partial derivative is evaluated from the context. Okay, so because this form will be more brief, more simple, and you can compare this chain rule with the single variable case. In single variable case, intuitively you can think of consoliding the du, and we obtain the right hand side is dy dx equal to the left hand side. Similarly, in our multivariable case, you can also consider this to be concealed. Okay, so this is why this result is called the chain rule. The reason is the same as the single variable case. Okay, now we will give a proof of this important theorem. This is very important proof. We denote A for simplicity to be the derivative of f at B, and the capital B to be the derivative of G at A. So since f and G are differentiable at B and A respectively, we have lambda from some low neighborhood of Rm, the origin of the Rm, the low neighborhood of the origin in Rm to Rl, and eta. Eta is defined in the R neighborhood of Rn to Rm, such that the limit is 0. K goes to 0, lambda k to the norm of k is 0. K is run in Rm, actually in the low neighborhood of the origin in Rm, and h goes to 0, eta h 0. H is in Rn. Okay. Also, f b plus k minus fb is ak, the derivative of f at b plus lambda k. And for g a plus h minus ga will be bh plus eta h. All these are from the definition.